Hello, my name is Arnold Filzer. Today, I'll tell you about sparse covers of minor free graphs and low-dimensional metric embeddings. So a sparse cover basically is a collection of clusters that covers all the balls in a sparse manner. Well, formally, there are three parameters, rho, tau, and delta. When rho is the padding parameter, tau is sparsity, and delta is the scale. And the guarantees are as follows. Every cluster in the collection of the clusters has diameter at most delta. So this cluster has diameter at most delta, this one, and so on. The second condition is that every ball of radius delta over rho, so rho is the padding parameter, so every ball of radius, which is a rho fraction of the diameter, maximum diameter, is fully contained in some cluster. So this green ball is fully contained in the blue cluster, and this ball is fully contained in the red cluster. And the final condition is that every point will be contained in at most tau clusters. So here, this green point is contained in at most 2 clusters. And this is a sparse cover. So if you have this property that your collection of clusters could be partitioned into tau disjoint partitions, like this one can be partitioned into the blue partition and the red partition, then we call this a sparse partition cover. It's not only a sparse cover, a sparse partition cover. And if in addition you can construct such a sparse partition cover for every possible scale delta, then it's called the sparse partition cover scheme, or SPCS. So usually delta is not really important, the scale, and we want to succeed on every possible scale, and the important parameters are rho, the padding parameter, and tau, the sparsity parameter. So sparse covers could be used for various divide and conquer algorithms. So basically, if you take care of every cluster, in particular, you took care of every local area. In Snap, there's some small blow up, and you get to cover and treat everything. What is known? So the first result was by Averbuch and Peleg, who showed that every n-point metric space admits a log n sparse cover. And they all have a general trade-off between the padding parameter and the sparsity. For Euclidean spaces of dimension d, or more generally doubling spaces, one can construct a sparse cover with padding d and sparsity also d log d. And there's also a general trade-off. So in this paper, we focus on the short spat metric of minor free graphs. And here, the previous result is by Krautgamer et al., who showed that every short spat metric of minor free graphs admits a sparse cover with sparsity r square and exponential, with padding r square and exponential sparsity. And this is based on the famous padding decomposition of Klein-Plotkin-Rao, or LDD. The main result in this paper is an improvement on that. So we get sparse covers with padding r and sparsity r square. So this improves Krautgamer et al. In both sparsity and padding. And we also can get exponential sparsity while getting only a constant padding. Okay, so let's go to the first application I want to show you into metric embeddings. So in metric embeddings, basically you have a metric space X, and you want to embed it into a simpler metric Y while preserving all distances. And in this lecture, we'll say that embedding F have distortion T if all the distances increase by at most, it does not increase, and decrease by at most a factor of T. So you're not allowed to increase anything, and the shrinkage is at most a factor of T. And in this context, L infinity is a universal metric space in the sense that any endpoint metric space, finite one, can be embedded isometrically into L infinity. That is, for every point x, you get some respective vector, and the distance between the two vectors in L infinity will be exactly the distance between the 2 points in the metric space. And note that in L infinity, the distance is simply the maximum distance in any coordinate. So this is nice because it's universal. However, the dimension is huge. So the dimension required for this embedding is basically linear in n. Matuszek showed that there's a trade-off. So one can pay for distortion to get smaller dimension. So distortion k, basically with polynomial dimension n to the 1 over k. And if you want to get logarithmic dimension, you need to get logarithmic distortion as well, right? And so this is kind of their result here. And this is tight, assuming Erdos-Gish conjecture up to second order terms. However, for minor free graphs, Krautgomer et al. Show that one can do much better. And specifically, one can get distortion R square while getting the number of dimension mean only log n times exponential in R. So if, for example, you get a planar graph, which is a K5 free, you can get constant distortion and log n dimensions. And this embedding is based on their sparse cover, which is based on the Klein-Plotkin-Rao sparse cover. We have some very nice properties, which they utilized to get this embedding. So it's not clear from here if given better sparse cover, you can get a better embedding. The second result in our paper is a meta theorem transferring from sparse partition cover scheme as PCS into a low dimensional embedding into L infinity. So if you have beta tau sparse cover, you can get embedding with dimension log n times tau times log beta and distortion beta. And now if you plug in this meta theorem into our better sparse covers, you get an improvement on the embedding of Krautgomer et al. So you can embed with distortion R and dimensions log n times R squared. So this is potentially improvement, it depends on R in the dimension, and quadratic improvement in the distortion. And actually, if you open up the analysis and tailor it a bit, then you get, using our second result, you can get distortion 3 plus epsilon, so arbitrarily close to 3, while getting log n dimensions times exponent in R now. So in the rest of the talk, I would like to tell you a bit about this meta theorem and about how we construct the sparse covers. So let's start with the meta theorem. So we have a metric space that admits a sparse partition cover scheme, and we want to embed it into L infinity. So now I'll describe you how I embed a single coordinate with respect to a single partition. So we fix some scale delta, and we take one of the partitions in the sparse partition cover. So this is this red partition here. And we'll have one coordinate with respect to this partition, which we'll define as follows. So for every v, we'll take into account the distance to the boundary. So this vertex is very close to the boundary. It's have a neighbor out of its cluster. So this is distance is 1, while this vertex u has distance 4 to the boundary. In addition, for every cluster, we'll sample some parameter alpha, which will be either 0 or 1. So 1 means that we'll take this cluster into account, while 0 means that we'll nullify the cluster in this coordinate. And the embedding in this coordinate will simply be the distance to the boundary times this parameter alpha. So this is the embedding. So for example, for u here, distance to the boundary is 4, and the cluster survive has alpha 1, so the value in the coordinate will be 4. While for this vertex z here, this cluster is nullified, so the value in the coordinate will be 0. So you can show using triangle inequality that no distance will ever increase in this coordinate. However, some vertex pairs will have some nice contribution. So consider a pair u and v, and let's say that the distance is between delta and 2 delta. And now we'll take the specific partition where u is covered, in the sense when the ball of radius delta over beta is inside the cluster. So know that in this specific partition, u and v will belong to different clusters. And this is because the distance at least delta, while it's larger than delta, while the maximum diameter is most delta. And now let's suppose that we've been lucky and we sample this alpha such that the cluster of u get value alpha 1, while the cluster of v is nullified. So now in the coordinate of this cluster, we'll get some non-trivial contribution. Indeed, the value of u will be at least delta over beta times 1, while the value of v will be 0. And overall, we'll get delta over beta, which is about beta fraction of the real distance. So we get some non-trivial contribution. Now, what's the success probability if you just sample this alpha? Is quarter, we need to have 1 here and 0 here. And now if we repeat it for all the partitions in this sparse cover partition, and do it log n times for each one of them, we'll take care of all the pairs at distance about between delta and 2 delta. Now, if you repeat it for all these possible distance scales, you'll get embedding with the distortion 2 beta as promised. However, we don't want to depend on the number of scales. And the main contribution in this paper is to show how it's possible to avoid this dependence. So we use some perfect free codes and some smart ideas there, but unfortunately, I don't have the time to go into it. Okay, in the rest of the talk, I would like to talk about how we construct sparse covers. And the main tool here is the recent buffered cup decomposition. So we'll start by describing the cup decomposition by Abraham et al. So this is a way to cluster a graph. It works for every graph. So it works as follows. We start with some point x1, and we grow a cluster, which will contain in the ball of radius most delta around this center. I'll not describe exactly how this is done, but think just a ball. Then the second cluster will have some second center, x2, and we take a shortest path to the all previous clusters that you can reach. This is called the skeleton. And we grow some cluster which is contained in the ball of radius delta around this skeleton. Now the third cluster has its center, and now we take the skeleton to be the shortest path tree, touching to all the previous clusters, so it's 2 clusters now. And we create a ball or a cluster which contains inside the ball around this skeleton, and so on. So we continue. Now suppose that this picture is like a planar graph, so x5 cannot reach the cluster 4. So we grow the skeleton only to the clusters that we can reach. And then again, we grow a cluster which contains the ball of radius most delta around the skeleton, and so on. Now the sixth point cannot reach the 5 and the first cluster, so it goes only to the second, third, and fourth, and so on. Now you can run it on any graph. However, what's special about minor free graphs is that the number of leaves in the skeletons is small. Specifically, you can show that if I can reach 2 previously created clusters, which we call supernodes, so if I can reach 2 supernodes, then they can reach each other. In particular, their skeleton touch. So if you will contract all the skeletons of everything that I can touch in my skeleton, you'll get a click in the minor. And therefore, if you are KR minor free, it means that the number of leaves is at most actually R minus 2 or R here. And this is a very useful property. Okay, so you can know that each supernode is like a ball around the skeleton, which in the skeleton is the shortest path tree with at most R leaves. However, the supernode itself does not have a small diameter, which is a problem because we want clusters from diameter. However, the supernode itself admits a good sparse cover. And why is that? So take this skeleton, and along each shortest path, add a net. So just take a bunch of points, a distance, at least delta between themselves, which is maximal, and take balls around all these net points, like here. So this is a sparse cover. Why is that? Because from a perspective of every point and every shortest path, the number of net points along the shortest path, distance most delta from me, is constant. And because there are only R such short paths, this will be sparse. So the number of clusters that they will belong to is only like order R. Okay, and so the bottom line is that it's enough to construct a sparse to cover using supernodes, and this will imply by itself a sparse cover. Okay, so these were our supernodes, and you can see that this construction of the supernode is like in a tree fashion. So each time we construct a supernode, it says like a buzzer, which was the last created supernode in that I can reach. So now we construct more and more and create this tree structure until we cover everything. And recently, so 1 year ago, Chang et al. Showed that one can construct this cup decomposition with an additional buffer property. So this buffer property is that is the following. So for every 2 clusters, which are ancestors of each other, like 4 and 16 here, and guarantee is that if they are not touching, like here they don't touch, then the distance between them could not be arbitrarily small, and specifically, the distance between them will be at least delta over R. Yeah? So there's some guarantee that distances cannot be arbitrarily small, and distance is with respect to the cluster when the ancestor was created, like at the time. So here the distance in this cluster is at least delta over R. And now using this property in our paper, we showed that from a perspective of every supernode eta, the number of unsettled supernodes and distance most delta is bounded by its most exponential in R. And given this lemma, now one can construct very easily a sparse cover as follows. So for every supernode, simply construct a ball around the supernode that radius at most delta. So like this is my supernode, the 4 here, and I construct a ball around it of radius delta. And we do it around every supernode, and we do it with respect to the cluster when the supernode was constructed. And this will be a sparse cover. So let's see why it's sparse cover. Like here, this is around the 8. You can see it doesn't touch the 4 and others. So what is a sparse cover? So from perspective of a vertex, I will only join the cluster in my ancestors, which are distance most delta, but there's only exponential in R number of them. So this guarantees our sparsity. And to get the cover, so consider some ball and look on the first time when some vertex belong to a supernode, not belong to a ball around the supernode, but actually belong to a supernode. So at this time, all the vertices in the ball are still active in a sense. And once you take a ball of radius delta around the supernode, the all will be contained in it. So indeed, you contain the supernode. And as a result, we get our sparse cover, which has a constant padding and exponential sparsity. Okay, so to wrap up, this is our result. We have like these two results here, considerably improving over Krauthammer et al. So basically what we saw is like constant padding and exponential sparsity. So actually right after this paper, there's already a follow-up that will be presented later today in stock of myself and Jonathan Conroy, where we improved the padding sparse covers by getting constant padding and polynomial sparsity. So this is exponential improvement. However, the diameter here is weak. While in the work represented here today in sausage, the diameter is strong. So the two remaining open questions here is first to close the gap between strong and weak diameter. So now there's exponential gap, and it will be very interesting to get the same result for strong diameter. And the second question is to get the best parameters possible. So maybe you can get better than 8 here, or getting better than R to the 4, maybe it's possible to get R, and so on. That's that. Thank you for your time.